Good morning and welcome to this postgraduate video course on advanced hydrology. In the last class, we completed the chapter 5 on surface water, and in that class we looked at the concept of travel time. Then we looked at what is the time area diagram. We looked at one example, an example we solved in which there is a rectangular paved area as the catchment, and we had to find out the isochrones, the inter-isochronal areas, or basically we had to develop the time area curve. We did that, and then I gave you a homework example in which you were supposed to find out the direct runoff hydrograph response from that time area diagram which we developed for the example problem. I hope you are able to do that. If there are any questions, you can contact me. Then we looked at certain geomorphological parameters using the topographic data. In the absence of any gauge in the catchment, we can use such geomorphological parameters to compare two catchments to get some idea about the behavior of the catchment, how it is going to respond when the catchment is subjected to rainfall event. Okay. With that, we ended that chapter, and what we are going to do today is we will start chapter 7 on unit hydrograph. Okay. What we will do in this chapter is we will look at a lot of things. We will look at the definition of the unit hydrograph, we will look at the definition of various response functions which are needed to understand this. Then we will look at how we can actually derive the unit hydrograph using the rainfall and flow data at certain river in a catchment, and then how we can use the optimization techniques to develop a unit hydrograph for multiple storm case. Up until now, we have been looking at the lumped model or the deterministic model under the steady state conditions, all right, and the unit hydrograph is something which gives us the response from the catchment under unsteady conditions, or it gives you the time distribution of your direct runoff response with respect to rainfall or subjected to rainfall when you have the different time distribution of the rainfall. So, what we are saying is that till now we discussed or we learnt hydrologic models that are simple or most simple in nature, that is, we looked at the deterministic, or I can say conceptual, lumped and steady models. Now, this chapter we will deal with or deals with deterministic, lumped, and what, and unsteady models. Okay. For example, in the last chapter we looked at the derivation of the expressions of flow depth and velocity from overland flow and in the channel flow, all right. Remember, they were for the steady state conditions, okay. That was the inherent assumption. When the sufficient time has elapsed, what is going to happen to the flow depth and velocity in the overland flow and in the channel flow, okay. Those kind of analysis is useful for the worst case scenario, okay. When you have continuous input of rainfall, let us say, what will be the worst case scenario under steady state conditions. But what happens initially, all right, as the time elapses from the beginning, that we would not be able to do based on the expressions which we derived earlier, okay. So, the unit hydrograph is a very important theory which was proposed in 1932 by Sherman, and this is something which is still used today in its earlier form or the original form. All right. So, it is important to understand this unit hydrograph, what it represents, how it can be derived and how it can be used in the practice. Okay. So, in this chapter this is what we are going to look at, and in addition we will study or we will need to look at what is called a linear systems theory, on which actually it is based on linear systems theory. We will also use our knowledge of optimization. I hope that you would know the basic concepts of optimization which will be assumed, and then also some statistics, some knowledge of statistics actually will be utilized to carry out some of the things. Okay. So, if you look at the linear systems concept, in the first chapter we had looked at the systems concept. All right. Then let us look back or review what is a systems concept with reference to this particular chapter on unit hydrograph. Okay. And then we will go to the linear systems concept. So, we had seen earlier that you have some input which is rainfall, right, in a systems concept that goes into your physical system, which is the catchment in this case, right, which we say is equivalent to a lumped and linear system in the case of unit hydrograph. All right. And then the output or the response from the catchment is what we get is the runoff. All right. And how does this look like? The runoff may look like this, and the rainfall you may have in this form. Okay. And this is basically your effective rainfall. Okay. So, this is the systems concept, and then if we look at what is called the general hydrologic systems concept, that is what we are looking at. Okay. We have seen that the rainfall that falls on a catchment, all right, where does it go? Well, it goes into many or different storage components in the catchment. All right. So, we have seen in the last chapter that the storage components are what? It could be interception, depression, subsurface, surface, groundwater and so on, soil moisture, right, and each of these different storages have different characteristics, right. So, the storage function is actually is extremely complex in nature. All right. So, what we do is we say that the amount of storage, in a hydrologic system or in a catchment like the one I have just drawn above, S is given by the integral continuity equation. No matter how complex the storage is, it will satisfy or it will follow the integral equation of continuity. We have seen that earlier. Okay. Because the fluid motion follows the law of conservation of mass. All right. So, we can always apply that, and then we say I am going to write this equation again. We have seen it many times in this course, right, I minus q, and this time we will number it as 7.1.1. Okay. All right. So, this is a key element in this equation when we are doing the rainfall runoff modeling or when we are trying to develop a unit hydrograph or some kind of catchment behavior. As I said, this S is consists of many components, they are interrelated with each other, the inputs and outputs may also be interrelated with each other. These relationships are complex, these are non-linear, they are dynamic in nature. So, overall we are looking at an extremely complex thing. Mathematically, this storage function can be expressed as follows. The storage function, the key in the rainfall runoff modeling is to be able to capture this complexity, the non-linearity and the dynamism in your natural process, which actually comes from this storage function. All right. So, the storage function in general can be expressed like this. It is a function of what? It will be function of your inputs and various derivatives, di over dt, d2i, dt square and so on. We can go all the way to nth derivative, and then also the output q dq dt, d2q dt square and so on, right. And let me say that this is your 7 1 2. Okay. So, basically what we are saying is that we are saying that this catchment behaves like a reservoir, okay, in which you have some input going in, which may vary as a function of time. It may have certain storage. This is the storage which is expressed by this equation 7.1.2, which is quite complex, as I said, and then you may have something coming out of it, q. All right. It is a very generic, very simple simile I am trying to draw here. This is like a reservoir for the catchment. So, this is the schematic that shows the simulation of the catchment using a reservoir concept. Okay. So, what we are saying is that the catchment behave like a reservoir in which there is some input, there is some storage, and what comes out is the outflow q. All right. And this storage is going to be the function of input as well as output, and there lots of derivatives. Now, when we are developing a model, it will depend upon the accuracy desired, how many derivatives of which variable we are going to consider in our modeling. All right. So, this is the general concept, where this function f is determined by the nature of the hydrologic system being modeled. Okay. All right. So, now you have the input available to us, the rainfall that is falling on the catchment I. Then I have equation 7.1.1, which is nothing but the continuity equation, let us say 7.1.1 here, and then I also have the storage function. Let us say I have assumed that it is a linear reservoir. All right. For a linear reservoir, we have seen what is the relationship between the storage function and the other things. It is S is equal to K times Q. We say that for the linear reservoir, the storage is function of only the outflow and linear, okay. But we can make the things more complicated. So, given the nature of your input, all right, equation 7.1.1 and 7.1.2 can be solved. All right. So, it is a mathematical problem now. Once we have said that your catchment is going to look like this as a function of this storage function, can be solved in two ways. What are those two ways? Well, the first one is what is called the method of substitution or the direct method. Method of substitution. All right. We also call this analytical method. or direct method. What do we do in this? Well, we find the function ds by dt. We have already defined our function s from equation 7.1.2. So, we can always differentiate that and find out the first derivative, right. So, we find out ds over dt using the assumed function given by equation 7.1.2, right, and then substitute into 711, which is your continuity equation, to get the differential equation I am going to use this as dE, all right, and then we solve the resulting, or I should say to get the governing differential equation or your governing differential equation here. Solve the resulting governing differential equation along with your boundary and initial conditions in your I and Q by direct integration or direct solution. Okay. So, this is called the direct method or the analytical method or the method of substitution. Okay. If you recall, we have seen a couple of examples of this using the continuity equation and different forms of the storage function. If you recall, in this course we have seen linear and quadratic, all right. So, in first case it was S is equal to K Q. We have found the governing differential equation in the form of the transfer function operator. We have already done that, all right. And also for the quadratic, in which we said S was equal to K 1 Q square plus K 2 Q plus K 3, all right. I think that was the form which is a quadratic polynomial, all right. So, we have seen all that. So, that was as far as the first method is concerned, which is the direct method, all right. We will not go too much into the detail of this. Then we have the second one, which is called the numerical or approximate solution or approximate methods. I am sure all of you know that there are certain situations in which the equations become extremely complex, all right, and we are not able to solve the system of equations or the differential equation we have analytically. Then what do we do? Well, we take help of numerical methods or the approximate methods. What are those? The finite difference methods, finite element methods, and there are newer and newer methods coming every day. But we will not go into the details of that. What we do in the approximate methods is that the space domain and the time domain, what we do is we discretize these domains. We use certain elements, or at each nodes we try to satisfy the governing differential equation, and then we keep on integrating or differentiating the basic equations, and then we try to find out the values of the variables at each node after applying the boundary conditions. Okay. So, in the numerical methods, what we do is the finite difference approximations of the derivatives in 711 and 712 are used. Okay. So, instead of direct values of these derivatives, we are using their approximations at certain discrete steps or points, I can say, it could be with respect to time or space, in time and then solved recursively. Okay. So, most of these methods are iterative in nature. When we say recursively means what? We would apply these equations, we will get started with some initial solution and then we will have to iterate or successively keep on doing the iterations, all right, and then we solve it recursively until certain level of acceptable error is reached, all right. So, this is as far as these two methods are concerned. The next thing we are going to look at is the concept of what is called a linear system. Okay. And in this linear system, what we are going to look at is the formulation which is given by Chow and Kulinda Swami in 1971. Okay. What they have done is they have taken a very general concept or general equation for the storage function, all right, and using that general storage function, all right, which is very general, we can take the values of certain parameters in that and solve any kind of problem. So, using this general storage function concept under the linear assumption or under the assumption of the linear systems theory, they have tried to derive the form of what is called the transfer function operator. Okay. So, we would look at that. What is that? Well, with this what they have said is S is equal to or is given by this equation A1q plus A2 the first derivative dq dt plus A3 d2 q over dt squared and so on all the way up to A n d n minus 1 q over dt square, all right, plus this is as far as the dependence of S on the q is concerned, and then we have the similar expressions for dependence of S on the inputs. So, you would have use another coefficients, that is b's, you will have b1i plus b2 of your di dt plus b3 d2i d2 dt squared plus all the way to let us say bm, I am using another subscript here, and then you have m minus 1 I over dt what m minus 1. Okay. This should be, excuse me, a n over dt n minus 1. Okay. All right. So, let me call this equation 713. All right. So, this is the general expression, all right, where let us define all these parameters or the variables involved in this. What are the A's, and rather I should say A's and the B's are what? Are the model constants or coefficients which have to be determined after calibration. Now, these constants or coefficients are, we are saying, constant. In this model, these are constant. What do we mean by constant coefficients? A model with constant coefficients is one which is not adaptive, all right. As a function of time or when more data is available, the values of these parameters or the coefficients will remain constant, all right. So, we say constant coefficients it is an important assumption to understand. What does it do? These coefficients make the system what is called time invariant. Okay. What is time invariant? I am sure when you have studied the unit hydrograph in your earlier classes, you have seen that the basic assumptions with the unit hydrograph theory is that the unit hydrograph theory is what? It is linear and it is time invariant. Okay. You take up any book on hydrology, you look up at the unit hydrograph chapter, these are the basic assumptions. So, what do we mean by the time invariant assumption? Well, what it means is that the coefficients of your model are constant, right. So, they do not depend upon the time. So, if you apply this model, once you have calibrated the model or once you have developed the unit hydrograph, you apply that model to the data, and those data may be in January, it may be in June, it may be in December, all right, you will get the same response, all right. So, the coefficients do not depend upon the time or they are time invariant, okay. That is what we mean by that. That is, the way system transforms the input into output. In our case, the input is rainfall and output is direct runoff, does not depend on time. Okay. So, this is as far as these definitions of these parameters or coefficients are concerned. Okay. And then you have S is the storage, Q is the outflow and I is the input. All right. Now, as per this linear system or the Chow and Kulanidhi-Swami's theory, what do we do? Well, we differentiate in order to develop this model, differentiating equation 7.1.3, okay. Which one? This one, with respect to time, of course, and then substituting the result for ds over dt in our original continuity equation and making slight rearrangements. All right. Okay. If we did that, what we are going to get is this equation, okay, which you should be able to verify very easily. A n dnq dtn plus a n minus 1 dn minus 1 q dt n minus 1 plus all the way to your a 2 d 2 q dt 2 plus a 1 of your a 1 of dq over dt plus you will have q coming from the continuity equation, right. All of that is equal to what, or let me write it here, is equal to I minus b 1 of your di dt minus b 2 of your d 2 I dt square minus all the way to minus of your b m minus 1 d m minus 1 of your I over dt m minus 1, okay, and then minus the last term was going to be b m of your d m I over d t m, okay. So, the mth derivative, the last one, and let me number this whole equation as 7.1.4, okay. Or In a compact form, I can write this equation as some function n of the operator d applied on q. Okay, that is the left hand side. If you see this equation, okay, this is equal to your some function of capital M of your differential operator d applied on I, and let me say that in compact form it is 715. All right, where I have assumed certain things here, where d is a differential operator which we have defined earlier as d over dt. Okay, and what is nd and md? Well, these are differential operators which have very complex form, and this form can be derived from this equation. Or let me write what is your n of d. If you think about it, well, it is going to be a n of your dn over dtn. All right, this is applied on q, so I am not writing the q here, plus a n minus 1 dn minus 1 dtn minus 1 plus all the way to a 1 d over dt. So, you see that. All right, anything else? Well, there is a q there, so there will be a 1 coming out. All right, so all of this actually you will be applying to q, and on the input you have m. What is that? In that case you have minus b m, the last term corresponding to the mth derivative dtm, minus b m minus 1 d m minus 1 over dt m minus 1. All right, and all the way up to b 1 d over dt. Anything else? Yes, there will be plus 1 also here corresponding to I, which comes from the continuity equation. Okay. All right. So, with this, the 7.1.5, all right, which is this equation, all right, can be solved or written as to obtain what? Well, q as a function of time is equal to what? From this equation, q will be nothing but this differential operator m d over n d, whatever that form is. So, it will depend upon what is the value of n and what is the value of m. All right, what values of these, the order of these derivatives you are taking, that will depend upon the complexity or the dynamism or the nonlinearity you are trying to model in a catchment. All right. So, depending upon that, the form of this m d and n d will be dictated. All right. So, you have that, and this is multiplied by your input function. So, this is a very general linear system model which was developed by Chow and Kolindaswamy, and let me number this as 7, 1 and 6, where let me define this transfer function operator. Remember, we had seen this earlier in your chapter 1 and chapter 2, okay, for the couple of cases, and this is the most general one, m d over n d, which is the transfer function. Okay. Now, one thing, one important just note I would like to make here is, this is a lumped model. All right. Lumped means what? We have seen earlier in the classification of the models is that what is the difference between a distributed and a lumped model? Well, in a lumped model, you are not accounting for the variations of your variables with respect to space. All right, you are accounting the variation of the variables with respect to time only. All right. So, we are saying that this is a lumped model, but this is unsteady, lumped and unsteady model, as the derivatives which are taken are with respect to what? Time only. In this case we have taken. Okay. And then equation 716 is the solution or represents the solution of a linear system, of a linear system. Okay. All right. Now, we have been talking about this linear system, right. What do we mean by a linear system, or why do we need to make this assumption? We know that the rainfall runoff process is extremely complex and it is non-linear, but modeling or developing a non-linear model is very difficult. All right. So, what we will do is we will look at the couple of basic properties of a linear system. All right. The assumption of linearity allows us to do certain operations on our solutions. Okay. And using those operations on the solutions, we can solve many complex non-linear problems with reasonable accuracy. So, that is what we are going to look at next. So, what we will do is we will look at these two basic principles of a linear system. So, any linear system follows the following two basic what are those? Okay. Well, I am sure you have seen these earlier. Okay. So, let me look at the first one, which is called the principle of proportionality. What is a principle of proportionality in a linear system? I am sure you know, if you have a solution f, all right, the principle of proportionality states that if you multiply that solution by a constant, okay, any constant, then that constant multiplied by that function or the solution will also be a solution to the original problem. Okay. So, if you have a unit hydrograph or if you have a solution, you multiply that solution by 2.3 or 5.4 or any number, then that is also going to represent the solution. So, if you want to write it down, what do we mean by that? If a solution f of q is multiplied by a constant, multiplied by a constant c, let us say c is some constant, the resulting function c f of q, all right, is also a solution. It is as simple as that. Okay. The second one or the second basic principle is what we call the principle of superposition. Any solution which is based on the linear systems theory also follows the principle of superposition. Okay. This also I am sure you have seen earlier. What is the principle of superposition? Well, let us say you have two solutions, you have found two different solutions f1 and f2 to certain problem. Okay. Then what you can do is you can superimpose those two solutions. All right. That is, if you add those two or subtract those two, so you do some kind of superposition process. So, f1 plus f2 will also represent the solution to the problem, all right, or to the same problem. Okay. So, if you want to write it down, if the two solutions, let us say F1q and F2q are added, I am going to say here, or superposed, the resulting function F1q plus F2q is also a solution. Okay. Now, what I am going to do is I am going to look at these two concepts or these two basic principles graphically. What do we mean by that? I am sure you have used these two principles in your undergraduate hydrology course in your unit hydrograph chapter earlier, all right, but it is important to understand various computations or various operations which we have done using the unit hydrograph, why we are able to do those, all right. So, if we look at the principle of let us say proportionality first, what does it do is it allows us to find out the direct runoff hydrograph, all right, from certain amount of rainfall. What is a unit hydrograph? I am going to look at the definition of the unit hydrograph very quickly here, because I want to demonstrate what is the proportionality principle, all right. A unit hydrograph is nothing but the direct runoff hydrograph response from a catchment due to what? Due to unit rainfall or unit effective rainfall. It could be 1 centimeter or it could be 1 inch or it could be 1 millimeter, all right. So, from 1 centimeter of rainfall, if it is subjected uniformly with respect to time and space on the catchment, right, what will be the direct runoff hydrograph? That is called your U or the unit hydrograph, right. So, this is your time and this is your DRH response, all right. So, this curve we are looking at is the direct runoff hydrograph response due to 1 centimeter of effective rainfall applied uniformly over space and time on the catchment. Now, if we want to find out what will be the direct runoff hydrograph, let us say due to x centimeter of rainfall or 2.3 centimeters of rainfall, then what do we do? Well, we use the principle of proportionality and then we say that all of these ordinates of the unit hydrograph we can multiply it by x, all right, without making any changes with respect to time, all right. So, the proportionality would allow us to use or get the direct runoff hydrograph like this, all right. These two curves are similar, the way I have drawn they may not look very similar, but you understand what I am trying to demonstrate here. So, this is the DRH due to x centimeter of effective rainfall, okay. So, you have a solution due to some amount of rainfall which is 1 centimeter. So, another solution which is the DRH due to x centimeter of rainfall also represents a solution of your system. The system is same, but the input is different, all right. So, you can apply that different input on the same basic solution. So, that is why the principle of proportionality allows us to find out the direct runoff hydrograph from complex terms, not the complex term, but the increased value of x. Now, this is as far as the proportionality is concerned. This is principle of proportionality. Right. Now, next thing we are going to look at is the superposition. Okay. What is superposition? As we have said, there are two functions f1 and f2, you just add them up, you get the combined response or some resulting function which is called f1 plus f2, you can say that is f3 or z or something. That also represents the solution of the system, all right, to a different problem. Okay. All right. So, let us say that you have one is this, let us say this is your f1q, all right. You have another solution which is, let us say, this F2 cube. All right. So, what we are looking at is we have two different direct runoff hydrograph responses from the catchment due to two different input impulses. Okay. These may be, let us say, 2 unit hydrograph. 1 centimeter of rainfall occurs at some time, it produces a DRH. 1 centimeter of rainfall occurs after some time, that also produces the same response. Okay. Now, how do I find the combined response? Well, I just add the corresponding ordinates at each time. So, the principle of superposition will allow me to add the corresponding coordinates at the same time and get the combined response. All right. So, what you will then have is the combined response. It may look like this. All right. Right. So, this is your F1 plus F2. Okay. Let us say it is some F. Due to some rainfall occurring at some time plus another rainfall impulse occurring at little later. All right. So, you are able to get the superposition. Now, you can have a situation in the real life where you need to apply the principle of superposition as well as the principle of proportionality together. We can do that. Okay. How do we do that? Well, let us say, let me first write the application of proportionality and superposition together. Okay. This was F1 plus F2 due to 1 centimeter of rainfall, but we may have a situation where, let us say, this is 3 centimeter of rainfall. All right, and this produces some response. After some time, you have, let us say, 2 centimeter of rainfall occurring, and that produces another response. All right. So, now you have F1 and F2. What is F1? Well, F1 is the direct runoff hydrograph due to 3 centimeters of rainfall. So, F1 has actually accounted for the principle of proportionality. So, there is a unit hydrograph in the catchment, right, and then you apply that with 3 centimeter of rainfall impulse. All right. That is what represents this F1, okay, on this graph. Similarly, due to the 2 centimeters of rainfall or some input which has a magnitude of twice or 2, that will result into DRH response F2. All right. Then what we can do is we can get a combined response that will start from here. All right. So, this is again your F is equal to, maybe I can say 3 times I1 plus 2 times I2, which is applied on your F, where I1 is the response due to the unit hydrograph, all right, at that particular time, and I2 is the response due to the second impulse. All right. So, this way we see that we can use or we can apply the principle of proportionality and superposition to solve very simple or sometimes complex problems. Okay. Now, what I would like to do is when we apply all these linear systems theory or the unit hydrograph or solve a complicated problem, then we will encounter or we will need to understand some 3 or 4 basic different types of functions. All right. So, the next thing we are going to look at is some or certain important or basic functions which we will need to define. Okay. All right. So, the first one of them is what we call an impulse response function. Impulse response function. Okay. What is a impulse response function? Well, graphically I am going to represent this as, if you apply a unit impulse to any system Okay. All right. So, this is your system. What you are doing, you are applying a unit impulse input to this system. All right. And then what comes out is what is called u t minus tau. This is called unit impulse response function. Okay. So, you have a system, you apply a unit impulse input to the system, the response of the system is given by a function which is called the unit impulse response function. All right. So, let us first look at what is this unit impulse function. Okay. It is important to understand that. All right. So, let me then say that if a system receives an input of unit amount applied instantaneously, all right. Let me put that in quotes, an input of unit amount applied instantaneously. What is this? This type of input is actually called unit impulse input. So, if somebody asks you what is a unit impulse input, well, it is an input of unit amount occurring instantaneously. All right. So, you dump 1 centimeter of rainfall instantaneously on a catchment, all right, or you apply a force of unit amount to a system. Okay. What will be the response? That is called the unit impulse response function. All right. So, let me complete this. In the brackets, I am going to say a unit impulse for this. At time tau. Okay. So, this unit impulse input is applied at certain time tau, then the response of the system at a later time t is described by the what? Unit impulse response function. And this we are going to denote as u t minus tau. Okay. Why we are saying t minus tau? Because t minus tau is the time lag since the unit impulse input was applied. Okay. So, if we look at this concept graphically, all right. So, this is your time domain, and then we say that you have some on the same graph, let us say you are representing I as well as the output Q. Okay. So, what we are saying is that if we apply a unit impulse, what is this? This is your unit impulse, all right. What is going to be the response of the system is going to be described by this function. Let us say the response is described by this function which I have just drawn. This is then called u t minus tau, all right. So, and this is your unit impulse response function. Okay. This unit impulse response function follows or also follows proportionality and superposition both. Okay. So, that you can do this, you have time here, let us say a 3 impulse is occurring here, it is this, an impulse of 2 is occurring here, the response is this. You can combine these two, it will look like this, all right. So, this is your combined response like we had done earlier. Okay. Now, let us look at some interesting examples of this impulse response function, all right. For example, first one is what is called the guitar string. Okay. We are looking at some examples other than hydrology first, all right. What happens when you touch the strings of the guitar? Okay. Let us say you are applying a unit impulse to the system which is called guitar. The response or the sound that comes out will be described by certain sound waves, which is called the unit impulse response function, all right. So, this concept is used not only in hydrology, but in many other physical and natural systems. So, one example is the guitar string. Another example is what we call this the shock absorbers of an automobile as it passes over the some pothole or speed breaker. Okay. Let us say you are sitting in a car, you are going, all right. Suddenly, you go over a hump, a speed breaker or a pothole. What happens to the shock absorbers of that automobile or that car, all right. Let us say some impulse due to the movement of the vehicle on the your speed breaker, what happens is some impulse or some force is applied on the shock absorbers, all right. So, they will have some response, after some time it will die down. So, that kind of response is also described by what is called the impulse response function, okay, which will be different in nature, of course. Okay. So, what I am going to do is, we have looked at these two examples which are not in hydrology, all right. In the next class, we would look at some examples or at least one example of this unit impulse response function in hydrology, all right, and then we will look at some more functions. So, I will stop at this point because I am running out of time, and in the next class we will look at some other functions.